Alright, let's take a look at the source-free RLC circuit in series. So we have our resistor, our inductor, and our capacitor all in series. There isn't a source here. Let's take a look at coming up with the initial and final values, as well as some equations in this circuit here. And again, this is going to be a second order circuit. Okay, so we know that the energy at time 0 that's going to be stored in the capacitor is going to be represented by V0 here, and then that's the current that's in the inductor is I0. So this is at t equals 0. Okay, and we want to solve for those. So let's represent these as V of 0 as 1 over the capacitance, and we want to integrate from minus infinity to 0 I dt, and that's going to equal to V0. And then I of 0 is just going to be I0. Okay, so let's go ahead and take these and derive the equations from here. So if we apply KVL across this mesh here, so let's go ahead and apply KVL. Okay, we're going to come up with R, resistance value, times the current, plus inductance, di over dt, plus 1 over c, the integral minus infinity to t, I of tau, d tau, all is going to equal to 0. Okay, so that's the voltage for the resistor, the inductor, and then the capacitance. Okay, so now we can get rid of this integral. By differentiation. Okay, so we want to differentiate this equation, and if we do that, we come up with this second order equation. We get second order equation, and that's going to be d squared I over dt squared plus r over L di over dt plus I over LC, all equals 0. Okay, so this is a second order differential equation, and again, this is why these are called second order circuits. Okay, so what can we do from here? We can further solve for the initial conditions, and we can just we did in the previous section. So we're going to have two initial conditions to solve this problem. So we need two initial conditions. We know that the initial current is given, so initial current is given. Okay, and then the first derivative of that current can be solved as a result. So then we can do the first derivative of the current can be attained, and that's going to be, so if we solve this, we say Ri of 0 plus L di 0 over dt plus V0 equals 0. Okay, or you can rewrite this as di of 0 over dt is equal to 1 over L negative R I naught plus V naught. Okay, so we got the initial condition of di over dt defined in this fashion. So we have I naught, and now we also have this. So based on the first order solutions that we had in the previous section, we can expect that the solution to this will also be exponential. So we can make that assumption. So we can make an assumption where, let me scroll up a little bit. We can assume, whoops, assume exponential. So what that means is we can say our I is going to equal to some constant a e to the st. Okay. So if we do that, now we can substitute this back into the equation, and then we'll get a e to the st times s squared plus r over L times s plus 1 over LC all equals 0. Okay. And then I'm going to skip some steps here. But essentially if you solve for this equation, you're going to come up with these couple solutions. You get these solutions. Where S1 is going to equal to minus alpha plus the square root of alpha squared minus omega naught squared, and S2 is going to equal to minus alpha minus the square root of alpha squared minus omega naught squared, where alpha is going to be defined as r over 2L, and omega naught is going to be defined as 1 over the square root of LC. Okay, so these are the equations we're going to be utilizing in order to solve for the second order circuit. So let's go ahead and save these. So we got S1 and S2, and then alpha and omega here as defined, which will be known as either our resonance frequency. So omega naught here is going to be the resonant frequency. Okay, and that's going to, based on this, we'll be able to determine whether we have an overdamped, critically damped, or an underdamped system. Okay, and our S's here, our S1 and S2 are going to be defined as our natural frequencies. Okay, and they're going to be measured in nipers per second. And you would see it as n sub p over s. Okay, that's the measurement unit for this. All right, and then the resonant frequencies are typically in radians. They're typically expressed in radians. Okay, and then alpha is going to be called the Neper frequency. Okay, so S's are the natural frequencies, omega naught the resonant frequency, alpha is the Neper frequency, and we're going to mainly be dealing with radians per second. All right, and let's look at a couple cases for these values. Okay, so when we have let's go scroll up here a little bit and look at these figures here. So a couple cases when alpha is greater than omega naught, we have an overdamped system. Overdamped system. Okay. So what does that mean? So our overdamped system is going to look like this here. This figure on the left side. Okay. In this case, both S1 and S2 are real and negative. So both S1 and S2 are real and negative. The response of the system is going to be defined as I of t equals A1 e to the S1t plus A2 e to the S2t. So this is the case where you have overdamped. So let's go ahead and highlight this guy. Okay, so when alpha is greater than omega naught, this implies that C is greater than 4L over R squared. Okay, so let's look at the second case. And of course from this we don't see any, we should not expect to see an oscillation. So should not expect to see an oscillation. All right. So let's look at the second figure here, where we have a critically damped system. Okay, so the second figure here, let's scroll up just a little bit, where we have alpha is equal to omega, alpha equals omega, omega naught, and that's critically damped. Okay, and the differential equation becomes, so we're gonna have d over dt e to the alpha t I is equal to a1, and the solution will be I of t is equal to a2 plus a1 times t e to the minus alpha t. So this is in the case of a critically damped system, and in this case critically damped means that C is equal to 4L over R squared. Okay. And there are going to be two components to this response. We're going to have an exponential decay. We have two components. We have an exponential decay and an exponential decay multiplied by a linear term. So, and then exponential decay times some linear term. Okay. And just as additional information, in this case, S1 is going to equal to S2, which equals minus alpha, which equals minus R over 2L, just as a side thing. Okay, and then we have our third case where we have underdamped. And our underdamped one is when we have alpha is less than omega naught, and each one of these, they correspond to the figure on the left. So in this case, this corresponds to that, this guy corresponds to this. Okay. Alright, so in this case, when alpha is less than omega naught, the system is considered to be underdamped, and then the solution for this guy will be I of t is equal to e to the minus alpha t times b1 cosine omega d times t plus b2 sine omega d times t. Okay, and we'll define what those guys are in a second. So let's just highlight this guy for an underdamped system. Let's go ahead and write this down here. Underdamped system. And this is for, again, we're looking at series RLC circuits. The figures on the left here, you see that we see some oscillations. In here, I'm going to scroll up a little bit, where J is going to equal to square root of minus 1, and WD is going to be the square root of omega naught squared minus alpha squared. Okay, this is for the underdamped case. Okay, so omega naught in this case is going to be the undamped natural frequency, and WD is going to be the damped natural frequency. Let's go ahead and write this down. This is going to be the damped natural frequency. Okay, and omega in this case is going to be the underdamped or undamped natural frequency. Okay. Again, you can see the figure on the left there. So a couple things with damping in RLC circuits or networks. The RLC, so let's go write this down. RLC networks can be characterized by the following. One, scroll up a little bit. The behavior of these networks is going to be captured by the idea of damping. So behavior captured by the idea of damping. So, and that's essentially the relationship between alpha and omega naught. The oscillatory response is going to be possibly due to the presence of the two types of energy storage elements. So oscillatory response is possible due to the presence of two two types of energy storage elements. And finally, it's going to be typically difficult to tell the difference between damped and critically damped responses. Typically difficult to tell the difference between damped and critically damped responses. And that's essentially a quick introduction to source-free RLC series circuits. We'll continue with the parallel circuits in the next lecture.